introduce the microphone?
Yes, yeah, thanks. So we come now to our next presentation, which will be presented by Olivier Perrotin on evaluating the extrapolation capability of neural vocoders to extreme pitch values.
Okay. Thank you very much. Hello, everyone. Thank you for attending this presentation. So we are going to talk here about vocoders, so systems that goes from acoustic features to speech waveforms. And when using them, there is often a speech quality versus generalization ability trade-off. On the one hand, if you're using DSP-based vocoders, you might have a limited quality, but a high generalization ability to many kind of acoustic features and speech waveforms. And on the other hand, with the introduction of neural vocoders, has increased dramatically the quality of generated speech, but at the expense of a strong data dependency, because of course it's using machine learning. And maybe because of that, most neural vocoders today are evaluated in their comfort zone, meaning that people are using homogeneous train and test data set, for example, LG speech. And this is true for the evaluation of newly proposed neural vocoders, but also on some papers that compared neural vocoders' performances. So even if neural vocoders has been used quite extensively for the past few years, it's still unclear to which extent they can generalize to unseen data. So of course there have been some research on that. One way to increase the neural vocoders' generalization ability is to train them on massive multi-speaker, multi-language, multi-everything databases, like towards universal vocoders. And that actually consists in extending that comfort zone as long as data and computing power are available. And my question is it possible to include the entire human voice variability in one training set without the need to extrapolate to unseen data? And having said that, I think it's quite reasonable to still try to make neural vocoder able to extrapolate to unseen data. So new architecture have been proposed, for example, to generalize to better to unseen F0s. And in that case, the evaluation is made by the global judgment of naturalness of utterances that are generated with modified trajectories. And one question that is remaining is how do these neural vocoders behave at a frame scale at the moment they receive an F0 that they have never seen during training. So I think there is a need for a tool to evaluate the extrapolation capabilities of neural vocoders to unseen values during training. And this is what we try to do in this paper by choosing to investigate the pitch parameter, hence the title, Evaluating the Extrapolation Capabilities of Neural Vocoders to Extreme Pitch Values. So we propose an evaluation methodology that consists of simple segmentation of a database that completely excluded ranges of F0 from training, and then see how synthesizers behave when they see this F0 during tests. And we evaluated 4 classes of neural vocoders: WaveRNN, WaveGlow, LPCNet, and parallel WaveGAN. So before talking about methodology, a quick recap on the neural vocoders. So you probably all know that WaveNet is the first one that has been proposed. It's autoregressive, so we generate one sample given the previous ones, and it's kind of slow to compute. So many other systems have been proposed to make autoregression faster. One example is to switch CNN with RNN. And then another group of neural vocoders try to simplify autoregression by reintroducing the source filter model in neural vocoders, or in vocoders. In that case, the source or excitation is predicted with the network, and then the filter is just extracted from the conditioning parameters that are bark or MEL spectrum envelope. And in this case, the F0 is usually provided explicitly through the system. Another category attempt to do parallel generation of samples to get rid of autoregression using normalizing flows or probability density distillation. And the last one also do parallel generation of samples, but this time using GANs that allows also to reduce model complexity. So of course, this overview is not exhaustive at all because there are new neural vocoders every day. But kind of an overview, and for our study, we picked one neural vocoder for each category, so WaveRNN for autoregressive, LPCNet for source filter autoregressive, WaveGlow for flows, and parallel WaveGAN for GANs. All right, so now let's talk about the methodology we use for evaluation. So as I said, it's quite simple. First, we excluded ranges of the investigated parameters, in our case F0 from the trained set. And then we looked at how the synthesis behaves on these excluded ranges during tests. So we took LG speech database again. so which is a 24 hours database of an English female speaker reading non-fictional books. And you can see the probability distribution of F0 on the top in dark blue here. And from that, we identified two ranges to exclude, which are the two tails of the distribution, the 4% of, 4% here of the lowest F0 value and 4% of the highest F0 values. Having done that, then we build a test set on the bottom in purple by selecting 200 utterances that had the most F0 values within these two tails. So you can see on the purple distribution on the bottom that the tails are overrepresented in the test set. And then we excluded this test set from LG speech and built two training sets. The first one is the unseen training set, where we took chunks of 800 milliseconds that didn't contain any F0 values from the tails of the full distribution. So you can see that the distribution stops right before the tails for the unseen training set, and it gave us 12 hours of training set. And as a baseline, we built a seen training set, which has the same size of the unseen training set, but which has the same F0 distribution that the full edge speed data set, so has F0 values within the tails. So we have 4 neural vocoders and 2 databases. So we trained all of these to have 8 models, and we generated the test state 8 times. And then we evaluated the speech output. So we did 2 evaluations, global evaluation on utterances, and then local evaluation on frames. And I'm going to start with the global evaluation. So to do that, we extracted the root mean square error between MEL spectrogram extracted from the original and generated signals. And so these are calculated on frames. So for an utterance, you have many error values. And from these, we extracted first the average, which is the global quality of the utterance, and then the percentage of outliers of MEL spectrogram errors per utterance, which gives you the percentage of local artifacts you have for each utterance. In addition, we computed the error between the F0 from original and generation to evaluate the pitch reconstruction, and then the percentage of voiced to unvoiced errors. So how many per utterance, how many frames were synthesized unvoiced while we were giving explicit F0 value. A voice, we were expecting a voice frame. So here are the results. You can see the 4 measures. For the 4 system, LPCNet, parallel WaveGAN, WaveGlow, WaveRNN, and each time you have 2 plots, the S for seen training set and the U for unseen training set. So if we look at that step by step, first, let's have a look at the seen training data set, which is a baseline, just to compare with previous studies. So you can see that the MEL spectrogram average is best for WaveRNN on the seen training set here. For the percentage of local artifacts, it's WaveGlow who has the least. For pitch reconstruction, it's WaveGlow who is the best. And for voiced to unvoiced error, it's quite the same for all systems on the seen training set. What I wanted to say here is that depending on the criterion, it's not always the same neural vocoder that is the best. WaveRNN is the best for average quality, and WaveGlow is the best for local artifacts. And I just want to say that this is something that is not really included in perceptive test. When you ask people which is the best, which sounds the most natural, you don't really know if the subject will focus on local artifacts or average quality. And this is something that could be included in future evaluation, I think. If we go to see the result for the unseen training data set, we can see on the MEL spectrogram average, there is, it's quite hard, kind of hard. There is not much difference on the MEL spectrogram average between seen and unseen training sets. So in average, it doesn't make much difference when there are some frames that are unseen by the system, but you have a strong local degradation. All system, the percentage of local artifact doubles when there are unseen F0 values in the utterances. You have also a F0 degradation for most systems except WaveGlow, and more unvoiced errors as well, except for parallel WaveGlow, which means parallel WaveGAN, which means that probably when the system see unseen F0 values, sometimes they prefer to generate an unvoiced frame. On the top of that, we did a subjective test, a MUSHRA, when 23 subjects rated 20 utterances on the unseen, from the unseen training set. And you can see on the plot on the bottom right here that parallel WaveGAN, WaveGlow, and WaveRNN were given quite similar rates. but that LPCNet is significantly lower than the others. And that correlates quite well with the lowest score of LPCNet for the percentage of local artifact and F0 degradation. So it means, or it suggests that subjects were sensitive while listening to local degradation in the synthesized utterances. So to conclude the global evaluation, there is no impact on global quality, but a strong local degradation of performance on the frames that had unseen F0s before. Of course, you have a degradation of the F0 reconstruction, and those local degradation were perceived during the subjective test by the subject. So this called for local assessment of neural vocoders to see what happened on those frames that got unseen F0. So to do that, we took all the frames of the 200 utterances from the test set and plotted the F0 reconstruction error, which is a distance between the target F0 and synthesized F0 in ordinates, against the F0 reconstruction difficulty, which is a distance between the target F0 and the median of the full database distribution. In a way that if we want to synthesize the median of the distribution, it might be quite easy because it's an F0 that has been seen a lot during training. But if you want to synthesize far away from the median, it means that it's an F0 that haven't been seen that much or maybe not at all during training. So it might be harder to synthesize. And this is in abscissa. So if we look at the result from the scene training sets on the top plots, you can see that for all systems, the errors are along the x-axis, which means that the F0 error is quite small, whichever the input value. So they are quite decorrelated, and it's what we want. And if we plot the correlation values and WaveGlow at the lowest, so WaveGlow is the more robust to any kind of F0 input on the scene training dataset. Now, on the unseen training dataset on the bottom, we can see three different behaviors. We can see that WaveGlow here behave quite similarly that in the scene training dataset. It means that it's still robust to any F0, even if some were unseen during the training set. Now, if we look at WaveRNN on the bottom right, we can see that on the left rectangle, which corresponds to the low tail that we excluded from the training set, you have a kind of uniform spread of errors on it. So it means that WaveRNN have slight failures, like random failures, with unseen low tail F0. And the third behavior is LPCNet and parallel WaveGAN here. And you can see that on the red rectangle, so for the unseen F0s, the errors is agglomerated along the empty diagonal here, and here. And that means that, so if you want to synthesize, for example, an F0 which is minus semitons for the median, but the error is plus 6 semitons, it means that it's right on the median. So it means that LPCNet and parallel WaveGAN, when they receive an unknown F0 value, they tend to synthesize the one that they know the best, so the one that they've seen the most during training. And the effect is strongest for LPCNet, and that might be because an explicit F0 input is given to the system, so this value is learned, it might make it more difficult to extrapolate new values. All right, so to conclude this paper, which has more questions than answers, I would say two things. First, the global evaluation of neural vocoders in their comfort zone usually misses the most interesting parts. And I think there is a need for local errors assessment, like average mel spectrogram, RMSE, or MCD, or NMOS are not sufficient. And then that the differences between the neural vocoders are accentuated outside of their comfort zones. And so there is a need for a careful control of train and test set to actually identify precisely the limits of the neural vocoders. Second point is that extrapolation to extreme pitch values is handled very differently by all neural vocoders. We saw that explicit pitch input might prevent good extrapolation with LPCNet, so there is kind of a control versus reconstruction quality trade-off. And that all these different behaviors, of course, means different responses for improvement that are yet to be understood to target the necessary and adequate response. Thank you for your attention. I'll be happy to answer your question.
So are there any questions here from the audience? Yes, please.
Yeah, can you hear me? Lots of questions, but I'll try to keep it short. The first question is, did you look at other pitch analysis methods besides the Pratt algorithm? Because I wonder how accurate it is in all these cases, and if that would have any effect.
In that evaluation, I only tried Pratt, actually. It does make some errors sometimes, like octave shifts and mostly octave shifts, or if you don't put the ranges of Pratt carefully, sometimes it's above the out of the range. I don't have my slides anymore, but on the distribution, after the 4% of the low tail, there were a lot of outliers that were F0 values which were too high and too low, probably errors of Pratt, or as well some creaky voice maybe sometimes. And I didn't use this F0 value that might contain errors in the annotation. I didn't exclude this F0 from the, I didn't use this F0 to make the unseen training set. It was on the train set, and and the test set as well, and I didn't look at explicitly these ranges of value while excluding my data to be sure that I excluded F0 values that were less prone to have errors.
Okay, and then my second question is, did you do any interpolation of unvoiced segments, or are the pitch values only for the voiced segments?
Only for the voiced segments.
Okay, and then when you look at your test set, I'm just trying to think about like what kind of an effect that could have on how many errors you could see depending on how many voiced segments there are in your test set or something like that. I don't have the kind of the ratio of voiced and unvoiced frames per utterance, but what you can see, for example, is it possible to put the slides back, or maybe not? So for example, we could see on WaveRNN on the local errors that it has a bit less error than the others, like LPCNet and parallel WaveGAN, which is much stronger, but it has much more unvoiced, voice-to-unvoiced error on the previous slide. So it means that WaveRNN might tend to ignore the new F0 value just to synthesize unvoiced frames, while the others they stick to voice, but putting wrong values instead. Yeah. This kind of behavior we observed. Yeah.
Okay, we also have a few online questions.
We have actually 4 questions from the chat, so we are not able to answer all of them. So please check the questions there after the session.
I can answer all
so I will try to pick the first one. Explicit F0 input does not mean that the model will use the F0 explicitly. So have you considered other vocoders that better use the F0? And there is some reference to some paper online on the archive. So just the question is, have you considered other vocoders that better use the F0? I don't.
Not yet. I mean, first what I want to do is try to understand why LPCNet is behaving like that, how LPCNet handles F0, and if I understood that correctly, then I can maybe switch to another one to see if it works differently and more adequately or not. I think.
So explicitly sign-based vocoder. Have you tried sign-based vocoder? It's in the question.
Yeah, not yet. Actually, that's maybe one of it doesn't fit in the 4 category I show. Maybe it's a 5th category. That one, this category I was missing. I think it would be great to, if I redo some experiment, to include this as well, because this one is quite relevant.
Maybe some other questions, which is very short. What is the average length of utterances?
It's LG speech. It's forgot 10 seconds. 10 seconds. Yeah.
Okay.
Yeah, we have time for one more question.
Maybe one more question. So it is counterintuitive to me that explicit F0 input in LPCN gives a worse generalization. Is the only solution to have diverse training data, which would be disappointing?
So can you say it's the only solution? That
you can read it for yourself. This one. It is counterintuitive.
So I don't know if it's the only solution. Probably there's this sign-based vocoder, maybe that might be another solution that is worth trying. But I think it's still worth, try to study LPCNet, understand why it's behaving like that. We have a little look at the pitch embedding, and it's quite interesting. Like if you take the pitch embedding and you do a PCA on it and look at the dimension, it's quite interesting to see that the second dimension ranks all the pitch values by order of apparition, of frequency of apparition of the training set. So LPCNet does learn which F0 has been seen a lot during training and the F0 that haven't been seen a lot at the training at all. So it might be a reason why it takes decision like that. So if we can observe that from the pitch embedding, maybe we can force it to be a bit different. I think there are many things to investigate on this vocoder and maybe others.
So we have to move on to the next presentation. So thanks to the speaker again.
Thank you very much.